a few people may still come in, but I think we'll get started. So it's my pleasure to introduce Andrew Yu, who was in the biostatistics unit. He was a PhD student here, but now he's off in Oxford, where he's a research associate, working with Chris Holmes and maybe some others as well. Okay, thank you. Please go ahead.
Thanks very much, Sean. It's great to be back. It's not working. Okay. I want to talk about some work I've been doing with Edwin, Chris, and Judith. All three of them I met in Oxford. And the topic of our project is something called semiparametric inference. And this is something that came about because we're thinking very deeply about causal inference. And so that was a kind of primary motivation for the kind of theory we're going to do today. So what is semiparametric inference? To put it simply, it's when the thing we're trying to estimate is low dimensional, but we don't want to restrict ourselves to a low dimensional model. So in other words, you have a finite dimensional parameter, but you don't want to use a finite dimensional model. So we're all very familiar with the idea of a parametric model. That's when both the parameter and the model is finite dimensional. And then for non-parametric inference, that's when the target and the model is infinite dimensional. So this is kind of like an in-between, and hence the name semi-parametric. Okay, so it turns out this kind of framework is now very popular for things like causal inference. Historically, things like econometrics and survival analysis is already kind of well known, but nowadays causal inference is really the kind of the hot topic that people want to use this for. And in particular, we'd like to think about semiparametric inference from a Bayesian perspective. So from my time here in the unit, I think a lot of people here are already experts in Bayesian inference, but for the benefit of everybody who may not be as familiar with the Bayesian framework, I should have a very quick primer of what we do in Bayes. So one of the angles from which we can think about Bayesian inference is that we start from a frequentist setup. So suppose we have some IRD data, and we believe it's drawn from some unknown fixed distribution P0. And P0 is known to belong to some set of probability distributions. So this is just what we might call the model in a frequentist setup. You could also think about P0 as a parameter, an unknown parameter, in which case this collection of distributions is just the parameter space. So with Bayes, we can conceptualize this as we add an extra ingredient. And that extra ingredient is a probability distribution, which we call a prior, actually on the parameter space or on the model itself. So now this P, instead of treating it as some kind of unknown fixed value, we treat it as a random variable. And it's distributed marginally according to this prior distribution. So now that we have a marginal distribution for P, along with a set of basic conditional distributions given P that generate the data, this gives us a full joint distribution on both the data and the parameter. So once we have a joint distribution and we've observed the data, we can then condition on the data, and that gives us what we call the posterior distribution on the model. So again, this is another distribution that's on the parameter space or on that set of probability distributions. So basically, we use the data to update our prior distribution, which may represent our beliefs on the parameter space, to a posterior distribution, aggregating the evidence that we see. Okay, but it's often the case that we're not actually interested in the whole data generating distribution. Right, so maybe we're only interested in some kind of summary of that distribution. So for example, it could be some kind of mean, quantile, or as I've alluded to, maybe it could be some just kind of like treatment effect, right? A causal effect. So in that case, with Bayes, we automatically get our inferential tool for any summary that we want. By the way, functional is just a kind of a fancy name for summary. Because once we have our posterior for P, this automatically induces what's called the marginal posterior of our function of interest, right? So let's say you've got your posterior for your whole distribution, that automatically gives you a marginal posterior for a mean or quantile or causal effect or whatever, right? It's there without any extra input. And once we have this marginal posterior, we can use it to compute all kinds of statistics. So if we want to do point estimation, then the most common statistics just use the posterior mean. So we take the average of our summary over the posterior distribution for P. Of course, there are other things you can do, posterior median or posterior quantile, etc. And for interval estimation, what you can do is actually use the probability sets of the posterior directly to quantify your uncertainty. So for example, let's say we want a 95% interval, then what we could do is just take some set of posterior probability with 95% probability. And we call that a credible interval. Okay, and I just want to mention a little bit about computation because it comes up later in the talk. So it turns out that with Bayesian inference, it's often the case that we can't analytically compute these posterior summary statistics. And so what we might have to resort to is to use some kind of Monte Carlo approximate sampling algorithm. So this is a very kind of rough gist of what we might do in a kind of Bayesian pipeline. So we have some algorithm, presumably, to draw exact or approximate samples from posterior. So the most common family of these algorithms would be something like Markov chain Monte Carlo or MCMC, but there are many other tools available. So once we have our samples of P, remember P is the whole data generating distribution, we can then just plug in P to that mapping, right? So this could be like now a bag of samples of our posterior means, the means of our distributions or causal effects or whatever. And this is exactly a sample from the marginal posterior that I was talking about on the previous slide. And then once we have that, we can then use Monte Carlo arguments to evaluate our summary statistics. So if we want the posterior mean, well, we just take the sample average of our marginal posterior samples. If we want a credible region, for example, what we call a central credible region, then we simply look at the quantiles for alpha over 2. So for example, we went 95% interval, we look at the 2.5% and quantiles, both upper and lower quantiles, and then use that to give us the credible interval. Okay, so that's my intro to Bayesian inference. The reason why we're interested in this, particularly from a Bayesian perspective, is that we noticed that Bayesian inference isn't particularly popular for semiparametric problems. And particularly it's not very popular for doing the kind of causal inference that people consider cutting edge right now. So before I kind of go into the reasons why that might be the case, I'd just like to kind of outline some reasons why we might actually be interested in doing Bayesian inference anyways. So one thing is that the prior offers us a natural way of doing regularization. Essentially, this means a good bias variance trade-off, right? Or we could also view it as a route for incorporating expert knowledge into our analysis, and that might give us a more precise or more reliable inference. But it also turns out that the non-parametric Bayesian algorithms have been doing really well empirically for a lot of problems, including causal problems. So, for example, this BART algorithm that I've got here, which is stands for Bayesian additive regression trees, have been doing really well for a lot of these kind of empirical comparisons of methods, outperforming things like neural nets, random forests, gradient boosted trees. And then something like Gaussian processes has been a very popular class of algorithms used in machine learning in industry. And the third thing I want to talk about is that a Bayesian model can adapt. So often we have lots of kind of these nuisance parameters that kind of like they relate to the regularity or the complexity of our model. And it might not be immediately obvious how we actually tune these things in both the frequentist and a Bayesian setup. And what we can do with the Bayesian model is we just take this as a parameter and then we put a prior distribution on it. And that allows us to automatically adapt to an optimal configuration using the data for these regularity and equivalence parameters. Okay, so those are the kind of pros, potential pros of using nonparametric Bayes in a semi-parametric framework. Unfortunately, there's a key issue which I'd like to try and illustrate. So this is a kind of toy problem, but it's it's something that does occur kind of in a quite widespread way. So let's suppose we have some data, again, IID data, and it's sampled from an unknown true density F0. And we just want to estimate a very simple summary. This is the integral of the density squared, or you could think about it as the expected density. It turns out this parameter is useful in a sense of you can use it for tuning. But for our purposes, it's really just a simple example that we can use to illustrate some of the issues that Bayes has. So if you were to ask someone who's very experienced with nonparametric Bayes, oh, could you recommend me some kind of model to do density estimation in a nonparametric way, then quite a likely candidate would be mixture models, particularly Dirichlet process mixture models. Basically, we take our density, we model it as a mixture of a family of densities, for example, with Gaussian densities, and then we put a prior on the mixing distribution. The specifics of this are not particularly important. I just want to kind of emphasize that this is quite a popular choice if you were just to do density estimation. And one of the other advantages of this is that the theory for this is very well known. So we understand the asymptotic properties of Dirichlet process mixture models very well now. By asymptotic properties, I mean in a kind of frequentist way is like if we get more and more data, the posterior will put more and more of its posterior mass, the probability mass, around the true density. So it's able to recover the truth as we get more and more data. It's kind of like an analog of consistency that we get in frequentist theory. Okay, but that's just about the whole density function, right? And we're not interested in the whole density. We just want inference for this one-dimensional parameter. We just want the integral of the density squared. And we'd like to know, how well does it perform for that? So as we discussed earlier, Bayesian inference has this kind of automatic plug-in property, which means once you have your posterior for F, which comes from this DPMM, for example, then we automatically get our marginal inference for chi of F. Okay. And so we want to investigate this marginal posterior. We want to find out whether the inference from this marginal posterior has good frequentist properties. So we just did a very simple simulation study. So we generated data from a Laplace distribution. So a Laplace distribution is when you kind of glue two exponential distributions together. So it has a little bit of a spike in the middle. That spike is kind of key to why we chose it, because it's not quite smooth at zero, this spike. So what we'd expect to happen if we use a Dirichlet process mixture model with normal densities is that you might over smooth where you shouldn't be smoothing too much, and that might incur a bias. So that's what we did. We generated data repeatedly from this Laplace distribution, and we just used a highly optimized routine from an R package. So here are the numerical results. So we have this parameter we're trying to estimate, and we've got point estimation summaries and interval estimation summaries as well. So we had 1,000 Monte Carlo trials. I want to first point out an interesting aspect of the point estimation, right? So here we've got the bias and the root mean squared error across these 1,000 trials. So if you're familiar with what goes on with kind of parametric statistics and the MLE, usually for point estimation, we'd expect the magnitude of the bias to be much smaller than the magnitude of, say, the root mean squared error. Basically, I mean, in parametric statistics, your bias tends to be like an order of magnitude smaller the things like variance and root mean squared error. But what we see here instead is actually the magnitude of the bias is quite comparable to the magnitude of the root mean squared error. Basically, if you think about the mean squared error in terms of a bias variance decomposition, right, there should be a contribution of the bias squared and the variance, right? In that case, here, the bias is actually making quite a sizable contribution to that decomposition of the bias variance, which is not something we usually expect from parametric statistics. So that might be a suggestion of why, when we look at the interval estimation, we have this 95% credible region. We want it to have approximately 95% frequentist coverage, but actually the coverage is quite a bit lower than that. So it should be 95%, but we only get about 80 something. That's quite a serious drop from what we'd like to have. And again, this may come back to this issue of the bias being quite large, larger than we'd want. So we can see this also if we look at the plots for the posterior mean. So both of these plots are when you have these Monte Carlo trials and you plot the value of the point estimator at each of these trials. So this is a kind of Monte Carlo histogram density of the sampling distribution of our point estimator. The vertical dashed lines, that's the true value of our parameter. Okay, so what we'd like to see is to have a distribution that's approximately centered around that vertical dashed line, right? But what we see is that actually there's this kind of downward bias, right? It's not quite centered there. The kind of bit that's where it peaks is not quite centered at that vertical dashed line. So again, this is an illustration of this kind of non-negligible bias, which gives us a clue as to why our coverage is bad. Okay. So let's try and kind of diagnose what goes wrong here. In a sense, the deep M and posterior isn't doing anything that it's not supposed to do, right? The aim of this kind of model is just to recover the whole density function, right? It's not targeting any particular summary of the density, it's just the whole density. And the density is a very complex thing, right? It's like an infinite dimensional parameter. So you don't want your variance to blow up. You have to do a bit of a trade-off and introduce some bias. Introducing bias here just means you're going to over smooth, right? You have a density that's too smooth. Again, this Laplace density is not quite smooth, right? But in order to keep the variance from blowing up, you need to make it kind of too smooth so that you get good errors for the density. Unfortunately, we're not interested in the whole density. We just want a good estimate of that chi functional. So this bias that we incur by over smoothing, it then bleeds into our inference for chi. Right, so this is what some people call a regularization bias, right? We've done this kind of trade-off with the bias variance, and it now kind of bleeds into the bit we're actually interested in. And that's why we see the bias on the previous slides. We have this not quite centered distribution around the truth. And this actually comes back to this kind of automatic nature of Bayesian inference. So some people kind of state this automatic nature as being a kind of key advantage of being Bayes, right? Once you have your posterior, you get everything in one go. But it turns out it might not be easy to get good inference for everything in one go, right? Maybe you actually have to tailor your inference to a particular parameter of interest in order to get something that's optimal. And this is what's happening here. We get good inference for F, but not necessarily for chi. This is not something that is restricted to Bayesian inference. It's actually a general phenomenon for non-parametric statistics, right? So if we have a good bias variance trade-off for like a whole complex object, like a density function, it doesn't necessarily translate to a good trade-off for some kind of low-dimensional target. So we don't want to say, okay, since this is a problem for Bayes, let's just leave it in the bin. We want to take advantage of these kind of good things that we talked about a few slides previous. So we want to use the adaptivity. We want to take advantage of the regularization of the prior. We want to use the predictive power of non-parametric Bayesian algorithms. So what we're going to do is simply add a step onto the end. So we're going to take the Bayesian algorithm without any kind of modification, and then we're going to wrap it around there's a really wrap around that algorithm, an extra post-processing step that will help us to kind of correct our inference. So just to illustrate what's going on, I'm going to go back to these plots that we had before. Remember, we wanted it to be centered around those true values indicated by the vertical dashed lines. That's from our initial posterior. We then do this post-processing, which kind of flattens the curve slightly, but now it's centered around the truth. And now if we look at the numerical results, so before we had this kind of large magnitude of bias, right, relative to the root mean squared error. Once we do this correction, we now see that root mean square error is approximately the same, but the bias is now much smaller. Okay, that's true for both sample sizes. And for the coverage, we've now also corrected that. So we had these 95% credible intervals. They now have coverage over 95%. So before I actually describe the algorithm, I'm just going to go back to the general setup. I need to introduce a few kind of preliminaries. So yeah, recall that we're interested in just some general kind of low dimensional estimand. Here I'm just going to take it to be one dimensional, but we can generalize it. Just a little bit of shorthand notation. So if I have a distribution P and I say it operates on a function H, I'm just taking the expectation of H with respect to P. And an important special case is where P is equal to the empirical distribution, which I've denoted by Pn. The empirical distribution is where you just have a point mass distribution that's only supported on your observed data with a weight 1/n for each data point. So if you take an expectation of H with respect to Pn, that's just taking the sample average of H across the observed data points. Okay. And I need to introduce an important concept from semiparametric theory. It gets a little bit abstract, so if there are any kind of questions, any queries, if anything's unclear, just ask. So for any of these kind of functionals, these summaries, it has associated with it something called an efficient influence function. And this is just a function that has mean zero and finite variance, right? It's some kind of intrinsic property of the functional. And the way I'd like you to think about this is that it's a kind of first order derivative of the functional. I haven't been very specific about in what sense as derivative, but let's, for the time being, let's think about it just as a first order derivative. Then in that case, if we were to look at the error between our functional evaluated at our starting point P, and then the functional evaluated at the true P naught, we want to think about if we can approximate this error, right? So if we think, okay, let's try and conceptualize some kind of first order Taylor expansion, because I've said this is like a first order derivative, then maybe we can approximate this error using this first order derivative. Okay, if this were true, then we might be able to take some kind of initial estimate or initial posterior and then use this kind of concept to debias that posterior or the estimate so that we get a better modified estimator or modified posterior. Okay, so let's think about it first from like a non-Bayesian perspective. So let's say you have a kind of frequenza style initial estimate p hat. So if you have an estimate p hat, then yeah, very easily you can just plug it in to your summary. So you have a plug-in estimate chi of p hat. But for the similar reasons that the Bayesian, naive Bayesian method doesn't work so well, this will also be biased. Okay. So what this suggests is that maybe we should take this estimate and then debias it using this heuristic from above. Right. So this heuristic suggests that we should take chi of p hat and then kind of minus the bias. Minusing the bias means you add this p naught, this expectation of the efficient influence function. Unfortunately, this is just kind of like, we just shifted the goalpost, we don't know p naught, right? So what we do instead, we replace p naught with the empirical distribution. So remember, that's this kind of point mass distribution supported only on observed data. Then this gives us what's called the one-step estimator. One step in the sense that it's like if you know about kind of the numerical analysis, like a Newton-Raphson step. Okay, we're using the derivative to kind of give us a modification. So that's where the name comes from. But for our purposes, it's just, you can think of it as a modified, improved estimator, right? So we're taking the plugin and we should get something that's better, less biased coming out of it. So the reason it's called an efficient inference function is because it has an intimate relationship with how well you can estimate the functional. So basically, the best precision with which you can estimate chi is determined by the variance of that efficient inference function. So if you have an estimator that is going to be approximately normally distributed around the estimator with variance equal to the efficient influence function, we say that is the estimator is asymptotically efficient, hence the name efficient influence function. So this is kind of the best case in the sense that the MLE is also the best case for parametric models. And basically, this one-step estimator will attain this best case scenario under much weaker assumptions than if you didn't do this biasing step. That's just the moral of the story here. If you do this debiasing, you'll be able to attain efficiency much easier than if you didn't. Yeah, so I mean, at the beginning, I kind of suggested that we were motivated by causal inference. So I'm just going to quickly kind of give you a more concrete example of where this kind of thing might be useful. So in causal inference, we often conceptualize the problem in terms of things called potential outcomes. So if we have this treatment variable, we want to find out kind of the average treatment effect, then we think about it as a contrast between functionals of, quantities involving y1 and y0, where y1 and y0 are the kind of outcomes that you would have seen under treatment control. I'm not going to go into too much details of kind of identification and things like that. If you're familiar enough with causal inference already, then this would be very boring. We're just interested in not the causal aspect, but rather the estimation aspect. So if you can ignore the causal stuff, what we're really interested in is there's some kind of complex functional chi that we want to estimate. And it's a combination of kind of different parts of the distribution kind of glued together. Basically, these kind of problems in causal inference are very amenable to the kind of semi-parametric estimation that people have developed. And all I want to say is that there are techniques of then taking a complex functional like this and then being able to give you the efficient influence function. So I'm not going to go into how you actually get this, but I mean, these are things that are already available in the literature. It's not a particularly simple form, but these are things you can do. Once you have this efficient influence function, then hopefully we can use this kind of heuristic that we had from a few slides ago, where we use this to try and debias some kind of initial estimate we have of the treatment effect. Okay. Right. So that was quite a lot of definitions. So I'd just like to kind of give you a breather and just summarize what we've talked about so far. Okay, so we're interested in semi-parametric inference, and that means we want to estimate a low-dimensional parameter, but we don't want to use a low-dimensional model. So we want to use a kind of state-of-the-art, maybe black box, heavily regularized kind of algorithm like neural nets or additive regression trees, but still get good inference for the low-dimensional parameter. So if we just kind of naively used nonparametric Bayes for these kind of problems, what ends up happening is that we have this regularization bias, from over smoothing or otherwise, which affects the kind of marginal inference for the function of interest. So we get this bias in the final analysis. So what I'm going to introduce very soon is a procedure that will correct the marginal inference of our target functional, in the sense that we remove bias and also get more correct coverage, and similar to those simulation results we had before. And I introduced this very important concept of an efficient influence function, which I've encouraged you to interpret as a first-order derivative. And we can use that first-order derivative to then approximate this bias, which we then remove from our initial estimator or posterior. Okay, are there any questions at this point? Either here or in the chat? No?
Oh, sorry.
Yeah.
No, go ahead, Brian.
If you're functional,
Yeah.
but you're interested in change, so it's, instead of looking at particular functional, you wanted to look at an expanded set of functional.
Yeah.
Does your efficient influence function change?
It doesn't change. Yeah. So each functional will have its own efficient influence function.
How does that impact on inference? If I were to interested in now going back to the
Yeah.
easier, the simpler functional, should I use the bigger, more expanded one, and then make inferences based on that, or should I go back to the just specifying an efficient influence function for the simpler one?
So if you have like a whole collection of functionals that you're interested in, each of them will have its own efficient influence function. So what you can do is start with the same common initial estimate. So you say, oh, I want to use random forest. Then you just, okay, I want to use random forest no matter what. But from that initial random forest estimate, I'm going to do a different debiasing step for each of my functionals. So you start with that and say, okay, for each of my functionals, I'm going to do a correction based on its individual efficient influence function. And that's going to give you one different estimator for each of the functionals you have. That makes sense.
Yeah. Don't you gain from those parameters in some sense of functionals are correlated?
Correlated, I mean, we're thinking about it in a kind of fixed way. So there's not exactly like a probabilistic correlation. But I mean, if they're similar in some sense, then the efficient influence function will also be similar, in which case the debiasing you do will be also not too different from the two similar functions.
I had a question which was very closely related to that. I had two questions actually, but one can wait till the end. And that was near the beginning, you said we're going to assume that this chi functional thing, this is it's just a scalar function.
Yeah.
And Brian's talking about you possibly being interested in more than one estimand. So wouldn't that be a case where? So I don't know what you do in that case, do you?
Oh, I see now. Okay. Okay. So it depends on what you want. If you want a simultaneous confidence interval for all your parameters, so you have a vector of different functionals. So chi is, as you said, no longer scalar, but actually a vector of things. So like you have simultaneous quantiles, for example, across the spectrum. Then yes, you might want a simultaneous confidence region that captures all of them with 95% coverage, for example. In that case, you need some kind of, well, you need an efficient influence function for the whole vector rather than like individual. So it depends on, depends on what you're looking at. If you do that, you generally need something that is kind of bigger in some sense than doing each of them individually. So it depends on, but I mean, that seems like
something that is bigger. What's something?
I guess if you looked like maybe the resulting rectangular confidence region from doing them individually, it's going to be smaller than all of them simultaneously. Which is kind of obvious, but it's so I mean that seems like actually a more sensible thing to do, because you want guarantees on all of them, or maybe I don't know if you do something multiple testing, but I mean it's probably that's a kind of separate issue. But yes, you would probably have some kind of joint efficient influence function. You would do that.
I don't think I've ever seen one of those.
I've not that common, I think. Usually people just have like a single estimand, like a single causal effect that they're interested in, and then they just do it on that. Most of it, I think the notation just gets a bit messy once people move away from the scalar case, and so it's just convention almost to stick with one-dimensional functions. Okay. Yes.
So not every chi functional can be derived have a efficient influence function, right?
Yeah, that's a good point. Not every. So basically, this efficient influence function depends. Well, actually, I said it already. It's a derivative, and so basically, the functional needs to be smooth.
So
I've been very vague about what it means to be smooth, but essentially, I mean, you can't be the case that if you just change your data distribution slightly, you contaminate it a little bit, then you completely change chi. If that makes sense, right? These things could get violated if you're doing like variable selection. You have something that's dependent on like a high dimensional covariates, and you do like the lasso or something like that, then you have this kind of sensitivity to perturbations of your distribution. So you can't change things. But the things that people look at in causal inference, generally, you can obtain an efficient function. And thankfully, people have already done the work in deriving these things, so we don't need to do it ourselves, we should look it up. Okay. All right, maybe I'll move on. So I'm going to describe our algorithm in the next slide. And I kind of done it in reverse a little bit, because I'm going to start off with how we actually compute the algorithm, which I think that's the more intuitive way of explaining it, and then I'll go backwards to the more formal definition later. So right at the beginning of the talk, I said that often the case with Bayesian inference, we have to do some kind of posterior computation. So we do something like MCMC, which gives us a sample from that posterior. So let's take that as our starting point, right? We have a bag of samples from our posterior. And then what we're going to do is we take each of these posterior samples, so P indexed by B, we're going to pair it with an independent draw of uniform Dirichlet weights. So if you've not seen the Dirichlet distribution before, we can sample from this distribution by just sampling IID exponential 1 weights and then normalizing them so that they sum up to 1. Right, so you can think about them as like a set of probability weights, right? Random probability weights. So we've done something a little bit peculiar here, right? So we've taken each posterior sample, we paired it with these probability weights, random probability weights. So we've introduced a new source of randomness here, right? It's independent. Yeah.
From a Dirichlet with
yes, that's right. Yeah. So it's a vector of n probability weights, something up to 1. What was I saying? Yeah, so we introduced a new independent source of randomness into our analysis, which might seem a bit odd, but there's some logic behind it. And then what we do is very simple. It's closely related to the idea of the one-step estimator that I introduced a few slides ago. We take the initial posterior draw, chi, and then we add the weighted average of that efficient influence function that we had before. The efficient influence function is evaluated at the posterior draw. I'll quickly go back to here, right at the bottom. This is what we did in the frequentist setting, right? So we had this p hat, we plugged that into chi, and then we took the sample average of the efficient influence function. So that's when, instead of having these random probability weights, it's just fixed 1 over n, 1 over n, 1 over n weights. Right, so that's what we do in the frequentist setting. Here, instead of doing those fixed 1 over n weights, we have these random Dirichlet weights. We take the initial thing that's already random, we add some more randomness in the second part. And that's it. These chi tildes are now drawn from what we call the one-step posterior. One step, again, it is inspired by the one-step estimator, which again is inspired by the Newton-Raphson algorithm. So that's the algorithm. So once you have this, this is what you saw in the simulation results where we had the kind of debiased posterior. So these uniform Dirichlet weights, if you're someone who's familiar with the Bayesian literature, this might kind of ring a bell. There's something called a Bayesian bootstrap, which is exactly what's going on here. So this is a more formal definition, but I mean, it looks a bit scary. It's just exactly what I've just described in the previous slide. Okay. So we have our chi of p. We add a new term, which I've called p tilde, the expectation of this efficient influence function with respect to p tilde. P tilde is a draw from the Bayesian bootstrap posterior, just in case you're someone who are familiar with this kind of stuff. So it combines these two independent sources of randomness, as I said. You have the initial posterior, that's just ordinary Bayes, ordinary non-parametric Bayes, and you have the Bayesian bootstrap posterior combined uncertainty. Okay. So I'll just go back to that simple example we had before, just to again illustrate what's going on here. So remember, we were interested in this integral of the density squared. And again, somebody else has done the work already. We can just use their form of the efficient inference function. So this is how we do the computation here. So we have our DPMM model. Suppose we already have like a working algorithm, like an MCMC algorithm. So we get draws of the density. Take each draw of that density. Then we pair it with these, this vector of random probability weights. And then we compute this thing, chi tilde. So it just follows this formula from above, right? And then that gives us a sample from a one-step posterior. This is exactly what we did when it came to those results I had at the first half of the talk. Okay, so now I'm going to be very kind of hand wavy or everything. I just want to give you a little bit of intuition, hopefully, in terms of what's going on. Why does this help us? I've already given you a kind of interpretation in terms of this kind of Taylor expansion, but maybe it's easier to show it geometrically. So let's say we have some draw from our posterior. All right, we have some kind of posterior sample of P. Here I've just called it P, right? We want to start at P and then get closer to the truth P naught, right? We have a starting point. We don't know the truth, but we'd like to get closer to it. So we think about the path that links between P and P naught, right? So here, these are just mixture distributions, right? You have like a probability epsilon, you flip a coin with probability epsilon of getting heads, then you choose P naught, 1 minus epsilon, you choose P, right? So P epsilon is like convex combinations of P and P naught, right? Geometrically, I mean, it's getting a bit abstract, but you can think about it as like a line inside your model or your parameter space. This line, if we then map it through this functional, this chi thing, this now gives us a path inside the space for chi. Right, so we've taken a path in distribution space. This now gives us a path in the chi space. Usually it's not going to be linear because chi is going to be some kind of complex combination of factors from P. But we start from epsilon equals 0, which is at P. We'd like to be able to go along this path to epsilon equals 1 because that's where P naught is. So we want to start at P and get towards P naught. And this is what this diagram is kind of showing you. The x-axis is epsilon. So if you go right to epsilon equals 0, that's our posterior sample. One of our draws from the posterior. We'd like to be able to take that solid blue curve to the other side at epsilon equals 1. If we're able to do that, then we completely remove the bias, right? There's like no estimation error. Unfortunately, we don't know this path. It depends on what the truth actually is. But what we might do instead is approximate the kind of best linear approximation to this curve. So that's the tangent to this curve at epsilon equals 0. That's the blue dashed line. So maybe if we don't approximate the whole path, if we could approximate that tangent instead, and we follow it along to the other side, it still gets us closer to the truth, right? So we started with quite a big bias on the left-hand side. If we follow that blue dashed line to the right, the bias is now much smaller. But unfortunately, again, we don't know that blue dashed line, but this thing is now much easier to estimate than a solid blue curve. So in particular, we can use this one-step idea to estimate that direction of projection onto the other side. So what we're doing with this one-step correction is basically kind of, we're thinking about which direction we want to fire our posterior sample in. If we do this kind of random Dirichlet weight thing, we actually get a distribution on the other side of where we end up at once we've done this correction. So that incorporates our uncertainty in not knowing what the true direction to go in. That's what this kind of extra randomness is doing. It's incorporating our uncertainty in not knowing the true tangent. Okay. So just to kind of summarize what I was talking about, the one step posterior is combining two sources of uncertainty. One is the uncertainty in the original kind of functional chi. And then given that starting point, there's also the unknown direction of tangent in which to project our posterior sample. And that's modeled using this so-called Bayesian bootstrap idea. So I don't want to go too much. Yeah.
The question before you move on. So in your sort of geometric interpretation, what would the step size represent? So you have the direction, that's fine.
Yeah.
What would the step size be?
In terms of the size of epsilon.
Yeah. Is it connected to your Dirichlet weights?
It's epsilon, you think of just like the size of a perturbation. So it's just a way to kind of conceptualize a derivative. You think about like the definition of a derivative, you think about a slight perturbation by epsilon and you divide by epsilon at the end, right?
Mm.
So that's just kind of like a way of kind of conceptualizing the idea of having some kind of error, but you approximate it with a linear approximation. That's kind of what derivative is doing.
Yes. Yes.
So that's the step size. I mean, it's not like a physical thing.
No,
it's just a way for me to represent what's going on.
But then when you do your correction, so you move slightly towards the true.
Yeah.
That's where the weights are doing their work, right?
Sorry.
That's where the weights kind of come in.
Exactly. Yeah. The weights come in because you don't know the best direction in which to move in.
Yeah. All right.
So the weights then give you your uncertainty in not knowing that true direction. So your final posterior combines that uncertainty with your initial posterior uncertainty.
All right. All right. Yeah.
Yeah. Because if you would just do that correction without the weights, you would kind of underestimate the uncertainty. Sure.
Why, apart from the fact that it's what happens in the Bayesian bootstrap, why draw the weights from a Dirichlet 1, 1, 1, 1?
Yeah. Yes, but basically it's because Bayesian bootstrap is derived from this Dirichlet process idea, and they're basically the simplest non-parametric model that gives us correct uncertainty. If that makes sense. Starting to get maybe a little bit technical, but I mean basically a Dirichlet process satisfies something called a non-parametric Bernstein-Mises theorem, a non-parametric a Bernstein-Mises theorem.
Okay.
But a non-parametric version of it.
Okay.
Basically, it's like it is bootstrapping. So it gives you the correct uncertainty. In the case of estimating this tangent, we don't need any kind of additional smoothness, and so Bayesian bootstrap is quite suitable. A Bayesian bootstrap isn't suitable when we need smoothness, so that might be when you're actually estimating the causal effect or a density function or something like that. That's why we can't use the Bayesian bootstrap in the first step. We can only use it in the second step.
Okay.
To be estimating ATE, you can't just plug in a Bayesian bootstrap to do that because you need to estimate regression functions or with propensity score.
Yep.
You can't do that with Bayesian bootstrap. But the second stage where you do the correction, you don't need any smoothness anymore. It's now easy. You can use estimating an expectation of this efficient inference function.
Okay.
So the first step is hard because it needs smoothness. So that's where you need your kind of black box machine learning algorithms to get close to the truth.
Yep.
And then you do this little correction. That correction is much easier to estimate than the initial bit.
Right. Yes.
That's where you can use the Bayesian bootstrap.
Okay.
Similar to in the frequentist case, you would just use the empirical distribution for the last bit because that bit's easy. You can just take a sample average. In the first bit, you can't use the empirical distribution.
See, I understand the debiasing aspect of this, but you're trying to achieve the right coverage asymptotically.
Mm-hmm.
So I was just wondering, I mean, could you use a Dirichlet 22222?
No, it wouldn't work actually, because a Dirichlet 222 it would be biased. It would be too concentrated.
Mm-hmm.
I mean, it's similar to work with that you do with Sylvia actually with case control stuff. In which case, if you have like an informative Dirichlet distribution, you basically learn too quickly from the data.
Okay.
So as you get more data, you're basically doubling your sample size, and so it kind of it gets very informative. You can use you can use informative Dirichlet processes because that has like a fixed amount of informativeness. But if you have like a 222, your informativeness grows with the sample size, and that's where things go wrong. Yeah, you can have informativeness as long as it's fixed with respect to sample size. So we can replace the Bayesian bootstrap with a proper Dirichlet process. That also works. But since we're not interested in using like informative priors at that point, because we're just doing a debiasing, we just use the least informative one possible, which also turns out to be the simplest and most computationally efficient. Okay, so we just use the Bayesian bootstrap. Yeah. Okay. I don't want to go kind of like dwell too long on the asymptotic theory. Basically, in the frequentist setup, what we'd like is some kind of asymptotic normal result, so then we can construct confidence intervals. What we do in the Bayesian setting is this thing called the Bernstein-Mises theorem, which is just a Bayesian version of a central limit theorem. So what we want is that we want our posterior to be approximately normal, and with the kind of correct variance, so that we get the right coverage in our credible intervals. This is just a kind of formal definition of what it means to have a Bernstein-Mises theorem. We have some assumptions showing how you can achieve it using the one-step posterior. And our conclusion is that you can achieve this result easier with the correction than without. Similar to the story before about plug-in estimation versus one-step estimation, it's easier to achieve the asymptotic normality if you do the correction. So again, I'm not going to dwell too much on this, but we kind of go into in the paper in terms of how we actually do how we do this, how we attain these assumptions. Maybe I'll just very quickly go through this. Basically, we wanted to test how well our method did, so we kind of retrospectively entered ourselves into this data analysis competition that was held at a causal inference conference in 2016. So what they did was they just asked everyone to like submit some code that they could then analyze on lots of these different data sets. They would be able to kind of modify the code depending on what data looked like. It's completely black box. And the idea was like, it's like kind of machine learning style bake-off, where they would then evaluate how well all these methods did at the end. So we thought, okay, let's try that because it's all very well documented. It's related to like an estimand we had before, but for our purposes, it's just a causal effect that we want to estimate from the data. And we use this Bayesian algorithm that's been doing very well, of course, the Bayesian to BART, Bayesian additive regression trees, which even the kind of non-Bayesians have been very interested in because it's been doing so well. So we thought, well, let's try that and then add our kind of one-step correction and see how well we do. Basically, the gist is what we have on the bottom are the different methods. So the methods that were entered before were in black, and the new methods in purple. So these are the results for point estimation across all the different settings. And it turned out that we managed to kind of do better than all the entries using this BART with the post-processing. We added this kind of, the result on the right is when we don't do the correction. And we see that the error is much worse. It was just a kind of way of evaluating the difference of doing this correction.
Let me ask, I would have thought the BART plus TMLE would be close to the answer that you got for the BART plus one step.
Well, so we're doing a very similar thing to TMLE.
But I suppose the uncertainty is not.
Well, so TMLE is aiming at the same thing, but it's doing it in a frequentist way rather than Bayesian way. So our kind of reasoning of kind of why it does better is because we're using more information from BART. So what they do in BART plus TMLE is they just take like a posterior mean something from BART and just plug it into their TMLE algorithm. TMLE is a very similar thing to one-step estimation that I talked about earlier. What we do is we actually transfer the whole posterior, and that we think gives us better performance. And that's also apparent when we look at the interval estimation. So so we had to kind of submit an interval, a 95% interval, and then it's evaluated according to how much coverage it has, which is in blue. So we want to be above that horizontal dashed line because that's 95%. If you're above that, then you've attained 95 conservative coverage. And then the orange is where you have the interval lengths. So ideally, you want to attain coverage, but with as short an interval as possible. So again, we're the only methods to actually attain 95%. And our intervals weren't much wider than what they had for TMOE. So we think it's this kind of additional kind of information from the posterior that's giving us better inference. And again, if we don't do the correction, we get much worse coverage. So this debiasing seems very, very crucial. Okay, just to wrap up. So yeah, if we like non-parametric procedures, we can still use them, but a naive application would generally suffer from bias and poor coverage. So what we want to do is take that non-parametric procedure and then add an extra step at the end, which debiases and corrects the shape of that initial posterior. Fortunately, this method is very fast. So the hard bit really is the initial MCMC. So the initial posterior sampling, that's going to be the hardest bit. Once you have that, it's actually very easy to do it because you're just sampling these IID Dirichlet weights. That's very, very efficient. So there are a number of things I haven't talked about today, but if you're interested, then please send me an email. Actually, I don't have it on here, but probably find it somewhere in the department. And we also have the preprints where we kind of go into things with a bit more detail. Okay, thanks very much for listening.
Thank you very much indeed. Very interesting. Do we have any questions? We've had a lot of questions. Andrew's done very well to finish at this time, given the number of questions that we asked him. But do we have any other questions in the room or online? I'll start with a question.
Yeah.
So this is Bayesian inference. Yeah. So typically one might want to use priors and performance of priors. So how does that fit into all this? Because this is really about asymptotic coverage of intervals, and it's not in a sense Bayesian coverage of credible intervals. It's frequentist coverage where you're thinking of the true value as being something that's fixed rather than drawn from a prior. So what would you say?
Okay, maybe I'll tackle the second thing first. So this is a very important point, which is like, kind of the utility of frequentist coverage to a Bayesian. I mean, I guess there are different ways of looking at it. But our conclusion was that if you use non-parametric algorithms, then it's impossible to completely have subjective informative priors. So there's always some kind of default element involved when you specify, say, Gaussian process or something. I mean, I don't think anyone's brain is big enough to have beliefs on an infinite dimensional space. So there's always going to be some aspect of it that's not completely informative. And so we need some kind of guidance in terms of kind of how well does the prior information wash out as we get more and more data. Yeah. And this is what the kind of results that we have kind of give us is that, okay, you can have your informative bit, and hopefully for finite samples, that will help you in terms of getting close to the truth, or closer to the truth than if you didn't have an informative prior. Right. So if you tune, say, your model for regression or density estimation in such a way that actually you're shrinking kind of closer to the truth, then your one-step posterior should also be kind of better in that sense as well, in a finite sample case. Okay. But we allow for the setting that actually you have so much data that you'd actually want your prior to essentially wash out, which doesn't usually happen in a non-parametric setting. That's the kind of problem with non-parametric Bayes, that often, even if you have lots and lots of data, the prior still hangs around, it still influences your analysis. In that case, it could be a problem because you would want the data to kind of take over and just speak for itself at that point, which it might not do. So what we'd like, ideally, for someone who uses this method, is to be able to incorporate their priors of choice, which would hopefully give them better finite sample performance, but also give them the assurance that there's you're heading to the right place, the kind of the optimal place in the end, if you have the kind of data.
What about if you if the prior, the informative prior that you want to use is an informative prior on, say, the average treatment effect in the treated, rather than an informative prior on the quantities that you need to estimate, that thing, that average treatment effect in the treated.
I think that's it's a very important problem, and it probably kind of, even without the correction, that seems like a very important thing to be able to incorporate. Yeah. So just generally in any kind of Bayesian setting where we have informative beliefs on some kind of, again, a function rather than the whole distribution. Yes. But then we're using some kind of non-parametric method that only models the whole distribution. Then it's a question of how do you actually incorporate that in a way that I guess kind of minimally affects other things, right? Because if you don't actually have informative belief about say other aspects of your distribution, you don't want to accidentally spill a lot of kind of informative belief into that. I think that's kind of something that's not resolved yet. In fact, I guess some of the work that I did with Brian and Rob was kind of doing that in a very specific setting. We're looking at this kind of exponential sorting where you're kind of targeting a particular estimand. It's not easy to do that in a causal setting because they're very complex parameters. So I don't know. I guess that's kind of like a unresolved problem.
Yeah. Well, thank you very much. Yes. Okay. No other questions in the room. And nobody's put anything in the chat. So if nobody puts anything in the chat in the next few seconds, then we'll finish. Right. Okay, then. Thank you very much indeed.